We've seen how L'Hopital's rule works with the two basic indeterminate forms of 0 over 0 and infinity over infinity. But what happens when we get an indeterminate form of 0 times infinity? And note that that's just the form of it. This could be negative infinity here too. That's still considered the same form. Well, when this comes up, there's a strategy, and the key is to divide by the reciprocal. Let's take a look at how this works. So we have two examples here. It says evaluate, and then for part A we have the limit as x goes to infinity of x squared sine 1 over 4x squared. Okay, well, how is this of the form 0 times infinity? Well, the first thing we do is just run this through and plug in infinity. If we did that, we get infinity here times sine 1 over infinity, which is sine 0, which is 0. So there we have our infinity times 0 form. It's an indeterminate form. But anytime you have an indeterminate form along with the limit, you're probably going to use L'Hopital's rule. So let's take a look at that. Well, there's a lot going on here, but the crux of it is really this part, this middle part in the box. So don't lose the forest for the trees here. And it basically says that the limit has to be 0 over 0 or infinity for L'Hopital's rule to work. That's one of the biggest mistakes I see with L'Hopital's rule is people forget that it has to be in this form to move forward. Then once it's in that form, then hey, yes, take the derivative of the top, the derivative of the bottom, and try the limit again. But we need to get it into the 0 over 0 or infinity form. 0 times infinity is not in that form, so we work to get it into that form. Okay, well, it says the key is to divide by the reciprocal, so I'm going to do that. So let's write this limit again. Limit as x goes to infinity. That sticks around. You just keep writing that limit as x goes to infinity all the way till the end where you actually evaluate the limit. And now I'm going to leave sine. You basically, sometimes it's hard to tell which one to make the reciprocal, but it's whichever one is simplest, essentially, usually. So I'm going to leave this sine 1 over 4x squared alone, and then I'm going to divide by 1 over x squared. Do you agree that that's the same thing as multiplying by x squared? It is, but make sure you can convince yourself of that before moving on. Okay, now what happens when we evaluate this limit? We get sine of 1 over infinity, which is sine 0, which is 0, over 1 over infinity. 1 over infinity is 0. 0 over 0 is indeterminate, but in a good way, because now we can use L'Hopital's rule. Check. Okay, then L'Hopital's rule tells us we can take the derivative of the top and the derivative of the bottom. Note that this is not the quotient rule, so I say equals by L'Hopital's rule. Limit as x goes to infinity. That's what that little h there is. You can use an LH. Okay, what's the derivative here? Well, derivative of sine is cosine. Cosine 1 over 4x squared times negative 1 over 2x cubed. Now, where did that come from? Well, I used the chain rule on the inside of this function here. So what's the derivative of 1 over 4x squared? Let's just do that on the side real quick. I'm going to rewrite it as 1/4 x to the negative 2. And we're doing the prime of that. Well, now we can see that it's negative 1/2 x to the negative 3. Okay, so that's where that came from. Down below here, we have the derivative of 1 over x squared is similarly negative 2x to the negative 3, or negative 2 over x cubed. So I'll just rewrite that here for simplicity's sake. Negative 2 over x cubed. And then look what happens. We get some cancellation. These x cubes cancel. So we now have the limit as x goes to infinity still. Still haven't evaluated that. How about this? Looks like it all becomes 1/4 here out to the front. Cos of 1 over 4x squared. And now we can evaluate the limit. We essentially put infinity in for x, or let x run out to infinity. That gives us cos of 0, which is 1. So this whole thing comes to 1/4. Okay, let's move on to part B. We have the limit as x goes to 1 from the left of 1 minus x times tangent pi x over 2. Let's begin by simply plugging in 1 from the left. That would give us 0 here, But as we approach 1 from the left, this becomes tan pi over 2, which blows up to infinity in this case. How do I know that happens? Well, I recommend having the graph of tan somewhere on at least easy recall from memory here, and note that pi over 2 goes like that. So as we approach from the left, tangent blows up like that. So we are of the indeterminate form 0 times infinity, which means we need to divide by the reciprocal. The question is, divide by the reciprocal of what? And it just essentially comes with experience, right? You do enough of these, you start to recognize which one to bring down and make the reciprocal. I'd say if you do something and then you do L'Hopital's rule and it makes it worse, then try taking the other one down for the reciprocal. At least that's one way to get by. I mean, you essentially have a 50-50 chance. So in the worst case scenario, you just spend a little bit of time going down the wrong path perhaps. But certainly make sure the thing that you take down to the denominator and make the reciprocal is something you can take the derivative of fairly easily. In this case, I'm going to use the tangent expression for my divide by the reciprocal. So let's take tangent down to the denominator as cotan. That's the reciprocal. So this becomes the limit as x goes to 1 from the left of 1 minus x up top. And then we have cotan of the same thing, pi x over 2. And now when we evaluate this limit, we get 0 up top and cotan of pi over 2, which is 0 as well. So now we are of the correct indeterminate form, and we can hit it with L'Hopital's rule, which means we take the derivative of the top divided by the derivative of the bottom, not to be confused with the quotient rule. It is not the quotient rule. Thank goodness, it's actually much simpler. Okay, so we have the limit as x goes to 1 from the left. Well, the derivative of the top is -1. However, the derivative of the bottom is slightly more complicated. We have negative cosecant squared of pi x over 2 times the derivative of the inside. Don't forget your chain rule there. So we have pi over 2 times pi over 2 down there. Well, let's clean this up a little bit. All right, we're still evaluating the limit, so I'm going to keep writing it. X goes to 1 from the left. These negatives cancel here, so we can make those positive. I'm going to bring the cosecant squared up as sine squared. So what we really have is 2 over pi sine squared of pi x over 2. X over 2. And now we can let that x go to 1 from the left. It actually doesn't even matter that it's approaching from the left. Sine of pi over 2 is 1. So this whole thing evaluates to 2 over pi. Now if we would have done this the other way and left tan pi x over 2 up top and then divided by 1 over 1 minus x, we could do that, but then we'd run it through L'Hopital's rule. We'd have a secant squared over, a bunch of stuff, and then we'd still get 0 over 0. So we'd have to apply L'Hopital's rule again, and you could start seeing it spiraling out of control, getting worse and worse with each derivative. So as soon as that starts to happen, back up and take the other term down to the denominator as the reciprocal.